Thank you very much. Krakow, actually, Poland. So I really planned to be in Belgrade, but planning nowadays is thoroughly, I don't know, disrupted activity, I would say. So unfortunately, I couldn't join you live in Belgrade. I apologize for that, but at least we will have this presentation. I guess an interesting discussion, hopefully an inspiring discussion of this thing. So I titled it, Uncertainty in Our Digital Lives, because I really think it's a topic that addresses us as human beings in the first place, except for the talk will be technologically focused. But then, we are the users of technology, and that is always about us, right? And especially when it comes to these new fancy things, generative AIs, large language models, I will be focusing on that in my talk. Only a few words about me. I'm currently a Chief AI Officer for SmartTalk, that's a Serbian-Dutch startup. We work in media technologies. We work with newsroom. We process tons of text, build recommendation systems for them, do data analysis, do machine learning for them, and similar things. In the media industry. And my background is, it was already noticed, I'm a data scientist. I have a PhD in cognitive sciences, psychology, and actually spent most of my life, I'm 50 now, most of the previous 30 years doing things like statistical learning, figuring out how to hack, how to reverse engineer the human brain and the human mind from experimental data. So pretty much that kind of life. And today, what's going to be the story about the following concepts, I will say. We need to say something about order, disorder, and predictability. Believe it or not, very crucial things for our lives in general, as I will try to show you. Then I want to relate those concepts with the concept of information entropy, right? And I will try to easily, as much as possible, in a simple way, explain what information entropy is for people with non-technical background, people who are not in STEM and who didn't learn information theory, because that entropy thing, that's, more often than not, it's like that teenage sex type of content, if you allow me to express myself in that way. So it's really talked about, but not many people really get it, what it is. And on the other hand, I will show you that it's really something very easy and a concept with a very wide application in your understanding of the world, not only of technology, data, and similar texts. And then I want to relate these concepts and the whole previous exposition to something which I believe could become a very serious problem when it comes to the data sets used to train these contemporary monsters like ChatGPT, like Anthropic Claude, Google Gemini, or Mistral's models, these large machines that can mimic human language and human intelligence up to a degree, because I don't know how disappointed you will be when I tell you that, but we simply only call these systems AI, but they're really light years away from being anything similar to natural human intelligence. But they're still very, very, very useful, and there is a reason why we started calling them AI systems now. In a way, they really do mimic some intelligent processes. Okay, so look, I have a question for you to begin with. So did you ever ask yourself how chaos and disorder are measured? Or did you ever at all assume that something which is disordered or found in a state of chaos can be measured? So let's take a look, for example, at this products of an AI system. By the way, I created this using the Midjourney generative AI system. It produces visual representations from text, from songs, right? So when you look at these 4 images, looks like abstract painting, like perhaps Jackson Pollock in black and white, this stuff, right? Whatever. We can see a mixture of regularity and irregularity. So it's not like a complete chaos. We can find some recognizable elements, even some symmetry somewhere, etc. But if we would ask ourselves, look, which of these things is more chaotic, right? So is there a way to measure that? Is it possible to measure the, order and disorder in any system in a way similarly as we measure length and time in physics or sciences in general, in practical life, right? So look, well, it is possible, but before we proceed towards that concept, the concept of information entropy, information at all, and relate it to the contemporary generative AIs and the data sets that we use to train them, we need a smallish technical introduction. Look, so I'm an analyst, right? And typically I analyze user behavior. And let's assume that I want to analyze user behavior on some social network, right? Okay. So I want to learn as much as I can about some user, right? By looking at when does that user clicks or reacts in some way on a social media post, okay? So I have 5 users here. Look, so user A, B, C, D, and E. And let's take a look at the first one. By 1, I will mark an event when a person liked something, so reacted something on a social media, right? Be it Instagram, TikTok, Facebook, whatever, right? So look at the first guy, the A person, they always click. Whatever we show them on social media, they always click, right? So once, okay. That one is easy, right? So look at the last one, the E user, it's all zeros, right? So that guy is simply looking at the social media, he never clicks on anything. Take a look at the user B, who is more often reacting than not, and at the user E, who is more often not reacting than reacting, right? Seldom he has once, which means he clicked, he did something, right? Most of the time, zeros, right? Well, it's not full zeros like E, but D is really only seldom, reacting only seldom, right? Now take a look at the user C, and approximately we will find 50% of time that person is reacting on something, and 50% of time that they're doing nothing. Okay. Now, a question that I would like you to ask yourselves is, who of these users, who of them are more predictable in their behavior and who are less predictable or unpredictable in their behavior? As an analyst, where will I face problems? But look, I mean, user A and user E are fully predictable. Like I can be almost certain from these samples that I'm looking at that if user A, if I show something to them on a social network, they will react, right? User E, I can be pretty certain that they will not react, right? Now, my odds in the prediction game are not bad for B and D because B reacts most of the time. So if I would have to make a bet, I would probably put my money on the prediction that user B will react on the next team that they see, as well as that user D will not. Okay, they will do nothing, most probably. User C is almost 50-50. They react half of the time. Can I predict the next step of user C? If I show them some social media posts, will those people click or will those people not click? Okay. Now, it's a very, very important intuition that we need to build here and to start understanding something. So look, ordered systems are predictable, right? Ordered systems. When you take a look at the user A and E, there is a simple rule describing them. They're ordered systems, right? The rule for system A, for user A, like, okay, so they always click. And there is a simple rule for E, like they never click, okay? For B, we can say they click with 85-90% of probability. For D, we can say they click with 10 or 15% of probability. But user C is problematic, right? Because that's a disordered system, and he's not really predictable. There is no rule, you know? It's like tossing a fair coin. 50% of times you get heads, 50% of time you get tails. And it's really difficult to bet on a fair coin, right? Now, look, describing order and information has to do with probability, right? So I was already using terms like, you know, most of the time this system behaves in that way, or most of the time that system behaves in another way. So now let's think about a game, a system, a user on social media, once again, who have actually 3 actions at their disposal. We can call this action, say, B and C. Okay, so A can perhaps be there is a new social media post, do nothing. B can be there is a new social media post, like it. C can be engage, you know, share, comment on the post, something else, right? And if we observe any system which can take a number of different discrete states, or back to my example, a user who can do 3 different things, right? Then, by observing their behavior for some time, we can assign probabilities. We can count how many times they do what, A, B, or C, and we can calculate what's the probability that that user will A, do nothing, C, engage, or B, simply like something, okay? So we can assign particular numbers. So we are measuring that probability, counting, okay? And one thing, important thing to remember about probabilities, they always sum up to 1, right? Okay, so we don't know if it's going to be A, which I assigned 0.45 or 45%. Is it going to be C with 0.28 probability, or is going to be B with 0.27? But what I know is that these 3 possibilities are exclusive. 2 of them cannot happen at the same time. 3 of them cannot happen at the same time. Only 1 can happen, so they are exclusive. And I know that I can add up exclusive probabilities of exclusive events to be precise, right? And they always need to sum up to 1. Now, that is interesting, but I really don't want to measure probability in order to describe the order or disorder in a system. I want to measure something else, which is called information, right? And in order to explain to you how entropy actually measures information, order, and disorder, right, I need to remind you of this following very simple psychological fact, and that is that we are surprised by low probable events, right? So low probable events in world at all, everything that surrounds us, those events are those that actually bring new information to us, right? Yeah. So if I buy a lottery ticket, which has an extremely low probability of bringing me, some significant amount of money. So look, if I win the lottery, my numbers come out tomorrow or this evening, right? So I will be very, very, very surprised. And the amount of information that numbers carry are huge for me, right? Okay. But if I buy a lottery ticket every week, and of course I don't get any money because my numbers don't go out. Why? Because it's a very, very minor probability that you can actually win a lottery, right? You will not be surprised, right? That's just the world as usual, as it is. You can say, okay, somebody's really, really lucky, but not me. There's 8 billion people on the earth, right? So picking who will win something by pure chance is very, very difficult, right? So let's talk about describing that simple psychological intuition that we are actually surprised by low probable events. Now, this is bad already, right? It's not really. This is high school mathematics, and you actually, I mean, it's very, very difficult that it has a low probability you haven't seen this thing in your high school education. Something simple, which is called a logarithmic function, okay? They can have these different bases, so-called. It can be logarithm with the base of 2, the natural one, which has actually a base of 2.71, the logarithm 10. In information theory, in entropy, in computer science, we typically use this logarithm with the base of 2, but all the conclusions will nevertheless be the same. You can use any of them. What I'm interested here is, I'm interested in the properties of this nice function, and only one part of this function. Look, you can see to the left, the x-axis spans from 0 to 1, the very beginning, and here below that, the logarithm function is negative. And since I want to use logarithm to talk about probabilities and describe what surprise and information are, I'm really interested in this part because probabilities can fall only between 0 and 1, right? Okay, so look, let's zoom in. Let's zoom in. And now, look, between 0 and 1, I want to place a probability of something happening, right? Now, look, a logarithmic function has a very nice property on that domain on that range between 0 and 1. Look, if something has a probability of 0, right, logarithm of 0 is actually going to be minus infinity. You can see how sharply the logarithmic function is actually decaying. It drops sharply as you get closer to 0, right? So that is a nice property. And another nice property is something has a probability of 1. A logarithm always has the value of 0. Now, what has a probability of 1? Certain events have a probability of 1. And if something is certain, a certain event, something is completely predictable, I don't want to be surprised by it, okay? But if the impossible happens, which is not possible, right? But if impossible happens, something which has a probability of 0, and that happens, right? I want to be infinitely surprised, right? Because the impossible happened, okay? And the only way to describe my surprise by impossibility is, I'm infinitely surprised. The only thing that I don't like here is this is the negative part of the function, so I have this minus signs here, and that is not really intuitive. And then there is an easy thing you want to do. You put minus in front of the logarithm function, and you simply turn it around, you flip it around, right? Don't worry, I'll have a nicer drawing than this, right? So surprise is something that we say in mathematics is the negative logarithm of probability. So minus log of probability measures surprise. Once again, just to make sure that we are on the same page here. Look, why is that so? All probabilities go from 0 to 1. 0 is not a possible event. That cannot happen. 1 is a certain event. You don't even have to predict it. 1 is the sun will rise tomorrow, let's say, okay? So if you put minus logarithm of probability here, there is a very nice property because this thing now becomes a description of how much information are you getting from any event. Because when you go with the probability close to 0, it will measure infinity. The impossible thing would be infinitely surprising to us, right? When you go closer to 1, and if you hit 1, that's a certain event, and the surprise or the amount of information for a certain event is 0. Okay, and then everything else falls in between with the property that as faster we approach 0, the amount of information is higher and higher, perfectly matching our psychological intuition that things with low probability carry a lot of information for us, right? They surprise. Very good. Now, I don't know what is the, who in the audience has a technical background or not, but, entropy once for all, because it's really simple. Look, if we understand what surprise and information are, now let's take a look at the whole system, a user that can do 3 things, and he can do A1, A2, or A3 with different probabilities. And here, what do? We just need to know these probabilities. We can measure them by observing their behavior, for example. Then we compute minus logarithm of the first one, the second one, the third one, and we observe 3 surprise measures, okay? Entropy, the information entropy, is nothing else but the average of these 3 numbers. You just sum up these 3 numbers together and divide them by 3, and that is entropy. And entropy is the average information, but it talks about the system as a whole, right? It talks about the system as a whole. Surprise. I'm surprised if a user does something highly improbable, but surprise measures the information of one state of the system, of exactly what he did, right? Entropy, as the average surprise, measures how uncertain is the system as a whole, how unpredictable is that user that I'm looking at. Look now, there is one very important property about entropy that we need to understand here. So look, this is some system A, and I have here a system B and system C. System C, the one which has 3 equally probable states. So all probabilities are 0.33333, 0.333, 0.333. Okay, so can I predict the behavior of system C? Very difficult, probably not, right? Okay. System C has the maximum possible entropy. When everything is equiprobable, that system is the most uncertain system above all, beyond all these 3, among these 3 systems, okay? So that one is unpredictable. If we would compute the entropy for the system C, that would be the maximum of these 3 numbers here. If you compute the entropy of system A and system B is obviously one with the minimal entropy. Why? It has one event, the first event, which is very highly probable, 2 states that are not highly probable. So this one is really predictable. System A is a bit more predictable than system C, but it's less predictable than B. It is easier for B to say what will happen, right? In A, well, yeah, one of the things is more probable than the second one more probable than the third one. So it is predictable in a way, but B is the one that we can easily predict, right? And never forget that. So entropy is technically, it's a very simple concept. It relies on high school mathematics, right? But it describes the whole system. Here's the famous equation. So the next time you see this and you think, oh, that information theory and entropy, that's rocket science. It's absolutely not rocket science. It's high school mathematics. The whole expression of information entropy here, it is just a compact way in mathematics to compute the average of 3 surprises, as I can just show you. Nothing else. I just like to have it. It's a famous equation, after all. Okay, now, how does this relate to the story about generative AI and large language models and the data sets that we use to train them? Look, these large language models that are so popular nowadays, like ChatGPT or Anthropic Claude or whatever you choose to use, they do only one thing, and only one thing exists in that operation. Given your prompt, so whatever you enter to a system, the system has only one task, and that is it will attempt to predict the next word. What is a good continuation of what you have entered as an input, right? So if you ask yourself, how do they respond by whole sentences and paragraphs? You send the prompt runs through a whole machine learning, a whole very huge machine learning model called the neural network. And the neural network spits out one word, one single word, even technically speaking, a piece of a word, which is called the token, but that is not important now. It gives you one word. What happens next is the system takes your prompt, adds the word that it predicted, puts it here, runs again to obtain the second word, and then the third, and then the fourth, and the fifth, etc., until you receive the full answer from the system. So that's the only thing happening here. Whoever thinks that this system somehow have a structure, understand the grammar of the sentences or anything similar to it, no, they don't. They just predict one single next word from a given prompt, and then they iterate until they produce whole sentences, right? So how does it actually work? Well, in a complicated way that I will not enter here, but look, so on the output side of these huge neural networks, right, there is something which is called the vocabulary. I will provide an illustration, don't worry. So you have a very huge machine learning model, okay, very huge, very complicated. You enter prompts here, right? The output layer, as we call it, the output layer is the vocabulary. It contains all possible words that can be produced at all. Right? And the task of the system is just to match your prompt and to analyze it so well that when the signals that travel through the system hit that vocabulary here, okay, so they will activate all words in the vocabulary. The goal of the system is to activate the correct word, the one that will naturally continue the sentence, right? So that is actually all that happens, right? So information run through the system, okay, in the end it hits the vocabulary, and it needs to activate something in the output layer. This is a very simplified representation. We have an output layer here with only 2 words, let's say, right? But in reality, it's the size of vocabulary. So you have, well, because we use tokens and not words, we have tens of thousands of output layer things in an output layer. But if we would use words, we would have millions, right? And that's everything that happens. Your prompt here it is coded into numbers. It runs to the model selects. It activates all the vocabulary. You need to find a word which has the highest probability of continuing the whole thing, right? So look, if we enter beautifully paired, the model A has this activation of the vocabulary, model B has this activation of the vocabulary, and model C has this activation of the vocabulary. Once again, I mean, really all the words that the model knows about will be active, okay? We are just looking here at probably, let's say, the most active words. So which model is the better? Which one is the best, sorry? Well, it must be model B, which is at the same time one with a minimal entropy. Why? Because this model activated the word cat, beautifully per the cat, right? Activated the word cat way more than dog or whale. Okay, so model A would get the correct response because cat has the maximum activation, right? But look, dog and whale are competing, and here dog and whale in model B are not really competing with the cat. So model B is still better. It has a more certain response, right? Look at the model C, it has a maximum entropy. This is not a good large language model, right? This one is confused. It says with equal probability, this sentence could be completed by adding cat, dog, or a whale. Right? So we would like to go to model A, which means something very important to us in this conversation. The entropy of this vocabulary activation is crucial, right? And also don't forget that we use human-generated data to train these models, right? And when I say human-generated data, we really use, you can really, I mean, you wouldn't be mistaken to think of the training sets for ChatGPT, Anthropic Claude, Google Gemini, and all these similar things, as of the complete history of the digital text available at all. That is what we are using to train. Like everything that we as a humanity have produced as digital text enters their training, unless we are talking about something so private that it could never enter the data sets, right? Okay, so look now what happens. Let's now talk about the usage of these models and what do we do with them. What is nice about large language models is that here to the right, we have a system capable of producing synthetic text, the outputs of the model, right? And because of that, because the system was trained with almost a complete history of the digital text, and it can mimic human language very nicely, right? So to the left, we have the user of the generative AI system that is now able to use all this knowledge, right? All this knowledge here. But there is a bad thing about it, and that is, so when we all start using generative AI systems, and most of the people I know use generative AI systems, right? What is going to happen is that at some point, we will begin to train more and more powerful system with a mixture of human data and generative AI syntactic data. Why? Because we will be using the products of generative AI. Those products will end up online. They will be scraped and they will enter the data set, right? And someone wants to train a better, more capable new version model updated. They will start reusing the data that were generated by the model itself. What happens in such situations? Well, we know this even before, we knew this even before 2024, but the thing is just two most recent studies, right? We find that a self-consuming training loop produces correct outputs. However, the output declines in diversity depending on the proportion of the used generated data. Fresh data can slow down this decline, but not stop it. Given these concerning results, we encourage researchers to study methods to negate this process. In other words, and here is a study just recently published by Oxford scientists in, I think, Nature or Science, Nature probably, who also established the same result. If you start training new generations of large language models, and this also holds for the model that produce visual outputs like Midjourney or similar, if you start training new generative AI models, but if you start training them on the data that they generated themselves in several generations of models, the models decline. Okay, they start producing rubbish, or they end up in a state where they always give one and a single prediction for whatever you enter. That is something which is technically called the model collapse, right? And that is, of course, that by entropy. That's the link with that concept. Why? Because look, I mean, if you train things on self-generated data, right, you're actually isolating the system. In this case, you're isolating a large language model from any sources of fresh information. Nothing new enters the system, right? Okay, and the system, however smart it is, it can only produce, as you can write only in one style, and that is yours, right? So the system can only produce the data from the structure of the system itself. It cannot really produce something new. It cannot self-disrupt itself, right? So that is very similar to entropy in thermodynamics, if you like. If you remember the high school physics, right? The second law of thermodynamics, which says any isolated system, okay, will spontaneously tend to maximum entropy, right? That's a so-called thermodynamic death. Something similar happens here, right? Now, here is the problem in relation to the whole concept and the context of this nice conference that we're having. So look, I mean, the problem is that we desperately need more data. We don't have them. And we are now facing this problem with possibly using synthetic data. And that can be, I think, very dangerous, as I showed you. So we are already using almost everything that there is to train these things, almost everything. OpenAI is running around all news agencies, publishing houses, and media in this world, trying to cut the contracts and provide more compute for them, okay? allow them to use their systems in advanced ways with more tokens, less limits, etc., in exchange for their news production in order to be able to obtain fresh data. That's a recent trend. It started happening this year. They already have contracts with several very, very large publishers, right? But that's not going to help because that is not enough. I mean, it's not enough. Even if we start writing data sets, training data specifically for them is not going to be enough, okay? So there is another thing. One could say, well, you know what? I mean, we can always intentionally prevent training new large language models by synthetic data, but there is a small paradox related to that. So, you know, I mean, we are constantly producing better and better models. And what else is a better large language model than the previous one, if not the one for which you cannot say whether its products are synthetic or human-bred, right? So a better model will be the one for which no other model can make a decision saying this is written by an AI or this is written by a human. After all, that is what we want, right? We want to hit artificial intelligence, right? So don't worry, because with these types of systems that we use now, we are definitely not going to discover AI in them, right? They are purely associative machinery. They're not symbolic machinery. It will not really work. But again, they mimic human language in a very, very nice way. So it will be increasingly difficult for all of us to manage the ecology of this data set. It will be increasingly difficult to say what is synthetic data, what is human-generated data. But if we let synthetic data back into the training of new and updated versions of the models, they will decay. We will observe an AI decadency, right? And that is the question with which I actually wanted to conclude my speech. I try to describe a problem which comes from my community of AI people, machine learning researchers, people who build these things and use them in our work every day. I'm not really sure that even I have the answer to this question, what to do about this problem, right? Of amassing this synthetic garbage that will enter the data sets. One could possibly say, well, you know, that's just a theoretical possibility, and God knows how much time will be needed for models to decay, right? And then we will figure out something before that happens. And the only response that I have for them is, you know, in 19th century, we started the Industrial Revolution, right? And pollution up to the level of climate changes, of global climate changes, was just a theoretical possibility, right? And look, where are we now, okay? So that is it, my dilemma, and I hope it was interesting to show you and relate all these concepts, but I have no answer to anything to conclude here. Just this open question that I would like to discuss with you. Thank you.